Assalamualaikum warahmatullahi wabarakatuh and good morning, Doctor. Today we will present our project titled Solar Voltaic Power Energy System for Electrical Vehicle Car Charging. My name is Aidil Nazri and my teammate are Muhammad Taqiuddin, Muhammad Amirul Qayyum and Muhammad Irfan Saidi. I will begin with the introduction and problem background. The adoption of electric vehicle or EV is increasing rapidly as countries move towards cleaner and more sustainable transportation. However, most EV charging stations still rely on electricity from the national grid, which is mainly generated using fossil fuel. This reduces the environmental benefit of EV. Malaysia has abundant sunlight throughout the year, making solar photovoltaic and solar PV are suitable renewable energy sources for EV charging. Therefore, integrating solar PV with EV charging system can provide cleaner and more sustainable energy. There are three main challenges. First, EV charging still depends heavily on fossil fuel generated electricity. Second, the increasing number of EV places additional demand on the national power grid. Third, solar PV is still not widely used in EV charging despite Malaysia's high solar potential. Therefore, our project proposes a solar PV-based EV charging system with an MPPT controller to maximize solar energy, improve charging efficiency, and reduce carbon emission.
Solar photovoltaic systems convert sunlight directly into DC electricity through the photovoltaic effect. Since PV output changes with irradiance, temperature, and shading, the system uses maximum power point tracking, or MPPT, algorithm to continuously operate at the maximum power point. Among the available methods, Perturb and Observe, or P&O, is the most commonly used because it is simple, requires low computational effort, and provides good performance under normal operating conditions. A DC to DC boost converter is used to increase the low DC voltage generated by the solar PV panel to a higher voltage, suitable for charging an EV battery. The converter operates using a MOSFET or IGBT switch, an inductor, and a capacitor, while the output voltage is controlled by adjusting the duty cycle. It also works together with MPPT controller to ensure the PV system always operates at its maximum power point, improving charging efficiency. Most electric vehicles use lithium-ion batteries because they offer high energy density, long lifespan, and excellent charging performance. The standard charging method is the constant current constant voltage, or CCCV protocol. During the constant current stage, the battery is charged at a fixed current until it reaches the target voltage. The charger then switches to the constant voltage stage, where the voltage remains constant while the charging current gradually decreases. This method improves charging efficiency, extends battery life, and ensures safe operation. In this project, a 7.2 kilowatts solar-assisted level 2 charger with a 400-volt DC output is proposed for residential EV charging. Different power electronic devices are selected based on their specific functions. In the EV charging system, a MOSFET is used in the DC-DC boost converter because it offers fast switching and high efficiency for MPPT operation. An IGBT is used in the DC inverter due to its ability to handle high voltage and high power efficiently. Meanwhile, a thyristor, or SCR, is commonly used in the controlled rectifier to regulate AC to DC conversion by adjusting the firing angle. Together, these devices improve the efficiency and reliability of the overall charging system.
Okay, we move to the methodology overview. Okay, this slide shows the overall methodology used to develop our solar PV EV charging system. First, we designed a complete system architecture and selected suitable components based on the project requirement. Next, simulation was carried out using MATLAB Simulink to evaluate the MPPT controller, inverter performance, and battery charging behavior. After obtaining satisfactory simulation results, we built the hardware prototype and conducted testing under different solar irradiance conditions. Finally, the system performance was validated by measuring voltage, current, charging efficiency, and overall stability. Okay, next, circuit design. Okay, this slide presents the circuit design of our proposed system. The solar PV panel supplies DC power, which is processed by the MPPT controller to maximize energy extraction. The DC-DC converter regulates the voltage before it delivers to the inverter for AC conversion or directly to the EV charging circuit. The battery management system or BMS continuously monitors battery voltage, current, and temperature to ensure safe charging. Protection features such as overvoltage, overcurrent, and short circuit protection are also included to improve system reliability. Okay, next we move to the technical specifications. Okay, this slide summarizes the technical specification and key features of our system. The design implements an MPPT algorithm to achieve maximum power extraction from the solar panels. An efficient inverter converts DC power into AC when required, while the battery management system or BMS ensures safe charging operation, safe battery operation by monitoring charging condition. Additional protection features help prevent electrical faults and improve overall system safety. Together, these technologies provide a reliable, efficient, and sustainable solution for solar-powered EV charging.
Okay, for the system result, overall the solar PV charging system achieved 94% peak conversion efficiency, with MPPT controller maintaining optimal power extraction across varying irradiance conditions throughout testing. For the peak power output, maximum recorded PV array output reached around 7.2 kilowatt under standard test conditions, meeting the target EV charging load demand with stable voltage regulation. For the full charge duration, complete EV battery charge 0 until 100% achieved in only 4.5 hours under full solar irradiance, with battery management system ensuring safe, balanced cell charging throughout the cycle. For the last one is a voltage stability margin. Output voltage regulation maintained within plus minus 2% tolerance under dynamic load conditions, and also confirming system stability and reliability across simulated real-world EV charging scenarios. Next, we will go through the system cost analysis. So for the solar PV panels, it used around 45% the cost, which is component at $2,800 for a 5 kilowatt array. Okay, so for the battery storage and electronics, it used about 25% of cost. Lithium-ion battery, bank and power electronics, including MPPT controller, inverter, and charge management system, account for approximately 1,550 ringgit of total system cost. So for installation and also infrastructure, it uses about 20% of cost, which is for the mounting structures, wiring, EV charging, interface hardware, and professional installation costs. Total about $1,250. Grid power alternative costs 3 times more in long-term energy expenses. For the payback and also savings, we got around 10%, which is estimate payback period is around 4 to 5 years, with annual savings of 1,500 in fuel and grid electricity costs. We move to the last slide, which is conclusion and also the future work. Okay, for the solar PV EV charging system, demonstrate reliable off-grid charging with high energy conversion efficiency, integration of MPPT control, battery storage, and smart charge management, validated, sustainable, grid-independent EV charging. The system reduced carbon emissions significantly compared to conventional grid power alternative. Alright, so future directions include scaling to higher power output, integrating bidirectional V2G capabilities, and deploying AI-driven energy management. Expanding battery storage capacity and exploring advanced PV cell and also technologies will further enhance system performance, resilience, and long-term economic feasibility.